Hello, everyone. Welcome to this workshop on AI inference workloads, solving MLOps challenges in production, presented by our guest speaker, Guy Salton. Guy is the solutions engineering lead at Front AI, specializing in the fields of DevOps, cloud computing, Kubernetes, containers, virtualization, CI/CD, and AI computing. He runs technical projects for commercial and enterprise customers, including on-site installations and workshops. Guy enjoys speaking at conferences and meetups around the world, as well as writing blog posts and delivering webinars. My name is Juan Carrillo. I'm a volunteer at TMLS, and just before we begin, if you have any questions, please ask them in the chat with a Q in the front so that the facilitator can identify them. And lastly, if you have purchased a summit ticket and are joining us for the talks on November 17 and 18, please look for an email from Hopin in your inbox today for early tomorrow. Hopin is the platform we use for the sessions, so please keep an eye on your inbox. And without further ado, Guy, please take it away.
Thank you very much, and thanks everybody for joining. So my name is Guy. I work for a company called Run AI, and I will talk about it a bit more in a few minutes. And today's talk, we're going to focus on AI inference workloads. So a bit about the agenda for today. We're going to start with some introduction of what is inference workloads, where does it fit in the AI models lifecycle. Then we're going to talk about some basic requirements for a model serving system. We're going to then see the main differentiators between how a model serving environment looks like and how it compares with the classic web serving environment. And then we'll also have some live demos. And I'll show you some stuff running. And of course, as this is a live workshop, like Juan said, please feel free to post questions on the chat and we'll try to discuss them and answer them during the talk. But we'll also have time for Q&A at the end. So feel free to interact. And let's begin. So as I said, to start with some introduction, if we think about the machine learning process at a very high level, it contains of three main steps, right? The first step is for preparing the data, right? And this can include things like exploring data, cleaning it, labeling data, and then basically creating data sets. And once we have the data set, we're ready for the next step of model training. So in this phase, in the middle, we will explore models, build models, and then run, model training at scale with things like hyperparameter tuning on the data sets that we created, on the first stage. And lastly, once our model is trained and verified, then we can move it into production so it can start serving requests from clients, from customers, and then actually provide some value and insights. So in this talk today, we will talk mostly about this last step here of inference in production. So after the model is already trained, how to properly move it to production and how to build a real-time serving system for inference workloads. Now, when we talk about inference, we first want to mention that we need to make sure that we understand that there's two different types of inference. You can refer to it as online inference and real-time inference. So real-time inference is when trained models are running on data that needs to be used by a real-time applications. An example of this are time-sensitive use cases like fraud detection, for example, where an online transaction needs to be approved or rejected, and time is of the essence here. as opposed to offline inferencing, which is when trained models run on a new collection of data. An example of these are time-insensitive use cases like image tagging. So for image tagging, the time isn't that critical, and we can run this even as batch scheduled workloads, where it will take a batch of images and on a nightly basis or every couple of hours, and it will just go and tag them each period of time. So this is offline inferencing, sorry. Today we will talk mostly about real-time inference. And for real-time inference, we need some real-time serving system to handle such workloads. We can't just run them on a scheduled, nightly session. They need to be processed, and they need to happen and provide some answers within some SLA, within some time period. So, for example, it needs to comply with some latency and throughput thresholds, and we'll talk about this later on. So again, this is the focus of today's talks, real-time inference. Now, it's important to understand that model serving is a completely different ballgame from traditional software engineering, right? So when we want to move models to production, this involves a lot of experimentation and research, and it will introduce new requirements and challenges that are different from just a traditional web serving application. So we will talk about some of the requirements for a model serving system, and we'll see how this is different from a classic web application that needs to serve requests. Here again, we're going to talk about a few of the requirements. Of course, these are just some basic requirements. There are other things that I can mention, like auto-scaling, like batching, and things like that. But for the purpose of today, we will focus on these three basic requirements. And this will also be the focus of the demo later on. So we'll start with a basic requirement, which is low latency. For those of you who are not familiar, the definition of latency is the time taken to process one request. So if you think about it, we are going to have some server that is going to host our machine learning model, and we are going to have incoming requests to our server, and we, for a model machine learning serving system, we would have some kind of latency requirement that will typically be set by the application SLA. So the application SLA will tell us that a request has to be processed within, let's say, 200 milliseconds. And this is the time, the maximum time that we want it to take the server to process the request and return a response. So this is low latency, and this is something that is also a requirement for any type of web serving application. This is not specific only for machine learning model system. And the second basic requirement is high throughput. And throughput refers to the rate of incoming requests that can be processed by a single server. So when we talk about throughput, imagine that we have some server, again, hosting our machine learning model, and it's going to run on some hardware resources with an associated cost. Now here, throughput, high throughput, or throughput in general, translate directly to the cost of our hardware resources, because of the deployment cost, you can say, because like we defined, a throughput is the rate of incoming requests that can be processed. So if we have high throughput or higher throughput, it means that our server can process more requests on the same hardware resources, which means, if you think about it, that high throughput also means that our server would be able to process more requests on the same cost, right? Because our hardware resources comes with some associated cost. So it is important that we have high throughput and we have low latency. But again, both of these requirements are true also for traditional web serving application and not only for model serving. However, our next requirement is more specific to model serving. So the next requirement is to maximize GPU utilization. And for those of you who aren't familiar with GPUs, as opposed to traditional commodity GPUs are a great fit for training machine learning models. And this is because they can help us run multiple requests in parallel, multiple processes in parallel, and this way they can digest a very big data set and run much faster than how you would run the same model on CPUs. So it's a great fit for model training, because model training is a very compute intensive workload, and that it can run for a long period of time, and it would run on usually very large data sets. But we also see so GPUs will help us get high throughput for training models. But again, in this talk, we want to talk more about inference. So for inference, running on GPUs, if you do it right, can also help significantly with getting low latency, getting high throughput, and also maximizing and getting optimizing the cost efficiency if you do it right. And what I mean by that is what we see many times with a lot of organizations that are running inference workloads on GPUs, even in production, is that many times they see very, very low GPU utilization. And numbers that we see sometimes, like you can see from the graph that we show here, is that we see a lot of times that the GPU utilization would be something between 20 or 15%, even 10%, which is very, very low. If you think about it, it means that between 80 and 90% of the GPU is wasted, is not utilized. And this is a shame. It can be a significant problem, because GPUs are also very expensive. So this very low GPU utilization problem comes with a cost. The reason that we see low GPU utilization is because with inference workloads, as opposed to training workloads, with inference, there is no back propagation process. So the processes that run as part of an inference workload are not as compute intensive as with training. So inference, that's why it typically consumes little memory and compute. So both on the compute, like I said, but also the memory footprint would be much, much lower. And another reason for that is the batch size. So if you think about it, that for model training, we would usually want to maximize the batch size as much as possible to get the highest throughput for our processes. However, in inference, the batch size is limited by the latency requirement, because if you increase the batch size more than some certain amount, then this will increase the latency too much, and it can breach our latency requirement, and this will breach our SLA, and it will not be acceptable. So with inference workloads, you would usually see pretty small batch sizes. You can't go too high. And this is another reason why the GPU won't be very highly utilized. Now let's think how we can integrate a machine learning model into a production environment. So the most straightforward and simple approach is to embed machine learning models into web servers. So if, for example, let's say, I think we have our web application, which already runs our business logic application. And the most simple and straightforward approach is to embed our machine learning model into the code of our business logic application, which is hosted by our web application. But the problem is that the requirements for web application and for machine learning models is different. They have different requirements, and that's why doing and going with this approach, even though it's the most simple way, it can cause very significant inefficiencies as well as very high costs, and I'll explain why. So the first thing is that classic web serving is often bounded by the network. We can have sometimes very high load of traffic. So the web application would be network bounded, as opposed to machine learning models that will be more compute and memory bounded. So this is the first difference. Second, traditional web applications that run our business logic will usually run on commodity CPUs, as opposed to our machine learning model serving our inference workloads that will run on compute or memory dedicated systems. So for example, new accelerators like the GPUs, like we just said, because running on GPUs can provide us with higher throughput, lower latency, as we discussed earlier. So this is another differentiator, right? As opposed to running on commodity CPUs, our machine model serving would need to run on GPUs. And also in terms of the throughput, a traditional web serving application can have high requests per second, while, like we said, our model serving usually would have relatively low requests per second rate. So the problem with this is, like we said, it's simple, but it can cause significant inefficiencies and also result in higher costs and lower performance. This, if you think about it, also introduces additional problems, because if we are now packaging these two and coupling these two together in a production deployment, then what happens when we have a problem in production, right? We have our application developer who is in charge of the business logic, and we have our machine learning engineer who is in charge of the machine learning model. What happens when there is a problem in production? Who do you go to? Coupling between the app and the model also introduces some additional challenges, like what do you do when you need to do updates and rollbacks and version control? These are two different components, and this becomes even more complicated when you have multiple machine learning models that are running in production, and you have multiple applications, maybe in a microservices architecture, using the same models, or maybe you have different microservices using different models. This can become very cumbersome and challenging. So that's why what we see these days, and it seems like this is a better approach, is to somehow decouple the web server running the business logic application from the actual machine learning model server. As these are two different components, each has different requirements, we want to decouple them. So the idea is that we will have our classic web server that will host our business logic application, and this will be in the responsibility of the application developers. And we will have our machine learning model that will be deployed in its own separate server in a dedicated real-time serving system, and this will be in the responsibility of the ML engineers, and the whole machine model serving system will be deployed and run through APIs. It won't be embedded into the actual web server running the business logic. So this would be a much more optimized and much more recommended approach. These days, the most popular way to train as well as to deploy machine learning models is using containers, and the whole data science ecosystem is built around containers. And the most popular and actually the de facto the standard container orchestration tool is Kubernetes. So what we did here at Run AI, as I mentioned in the beginning, I worked for a company called Run AI, and we built a platform, a compute orchestration platform for the AI era. So it helps both with building and training models, but also with model serving and inferencing. So what we did is we built a model serving system on Kubernetes, where you can have, and we help you manage multiple queues. You can have a dedicated queue for each service. You can set priorities between the queues and within the queues to help satisfy SLAs. And you can also define an auto-scaling policy for each service based on different metrics like GPU-based metric as well as load-based metrics. So what we did is we actually built a Kubernetes scheduler. So for those of you who are familiar with Kubernetes, Kubernetes was not designed originally for machine learning or deep learning. It was designed for traditional software engineering for deploying microservices. And that's why the default Kubernetes scheduler does not have many of the capabilities that we need for AI and for model serving. We will see some of the capabilities, additional capabilities that the Run AI scheduler provides on top of Kubernetes and can integrate with any Kubernetes cluster, and how this can help us with better running machine learning models in production, how this can help with getting lower latency, getting higher throughput, and reducing the deployment costs. See that we have a question. Was the Run AI scheduler built in-house or is it available as open source? So no, the Run AI scheduler is part of the platform, the commercial platform that we provide. It's not open source. It's a commercial tool. And of course, you know, we will see some examples of the capability that it provides, but if this is something that seems interesting, we can of course have a free POC and show you the capabilities, but it's not an open source tool. Okay, now let's go and see some live demos, and of course feel free to ask any further questions in the chat also as part of the demo. And again, we'll have some time at the end of the talk as well. So what we'll see in this demo, we're actually going to have two demos. The first demo, we're going to talk about something called MIG. So for those who are familiar with the new NVIDIA GPUs, the A100, it comes with something called the Emperor GPU architecture. And what NVIDIA did there is that they realized that, that for inference workloads, like we said, inference workloads don't really utilize a whole GPU. They don't really need a whole GPU. When you just schedule an inference workload on a whole GPU, it causes, you know, underutilization, and this results in very high cost and inefficiencies. So what NVIDIA did here is with their new GPUs and this new GPU architecture, they allow you to use something called MIG, multi-instance GPU. And this provides hardware slicing. So you can slice up the GPU to up to 7 slices. And this way, instead of allocating a whole GPU to your inference server, you can allocate only a slice of the GPU. So you can slice up to 7 slices and then run 7 models or 7 instances of the same model on the same GPU. You can also ask for bigger slices and then have the GPU partitioned into 2 partitions or 3 partitions. So, for example, and we'll see this later, but this is the NVIDIA terminology that they provide here. These are the different slices that you can request. So you can either request for the whole GPU and ask for this slice called 7G.40GB. It means all of the compute and all of the GPU memory that comes with the A100 GPU. You can ask for a slice of 4G, 20GB, which is 4/7, or 3G, 20GB, which is 3/7, or 2/7, or 1/7. And this is a great capability because it allows you to run multiple workloads on the same GPU and get better utilization for each of these workloads. However, it does introduce some manual and static limitations. So the main problem is that in order to work with MIG, these partitions are happening on the node level, meaning that the admin of the cluster of the GPU needs to choose some preset profile. The profile defines the actual partitions. So a profile can say, I want 3 slices of 2/7, and that's it. And then the researchers, the users that would want to schedule and run their workloads on these slices, they would have to work with these existing slices. So if this was the profile that was chosen, like 3 slices of 2/7, they won't be able to run a container on a slice of 1/7. They will only have these slices of 2/7. And if they want to run on a slice of 1/7 or 3/7, something that does not exist on the current profile, they would need to reach out to the admin. The admin would have to choose a different profile. And when moving to a different profile, he will need to drain all the running workloads. So this is a bit of a manual thing, and it can be a bit cumbersome and make the work of the researchers a bit more manual and annoying. What we did here at RunAI, and this is something that we worked on together with NVIDIA, is something we call dynamic MIG allocations. And this means that with every job that a researcher runs, so let's say a researcher has a machine learning model server that he wants to deploy, and he wants to allocate only a slice of the GPU, he can apply and deploy his server and ask for any MIG slice that he wants, and the MIG slice will be provisioned on the fly on the job submission rather than on the node provision. And this means that once the model once the job, this is not only for inference, but both for inference and for training, once the container is completed, then any additional job can ask for any kind of slice, and again, it will be provisioned on the fly. I see another question, can we use GPU slicing when deploying with Salton and KServe? Yes, this is a great question, and we see these systems gain more and more popularity. We are now also working, I think, I need to check, but I think this should be released very, very soon. We'll support also both Salton and KServe of Kubeflow. And now I want to show you a live demo of how this works. So let's start with the demo. What we will see is that first step, we will go and run 3 instances. So I will run 3 containers, and for each container, I will ask for a slice of 2G, 10GB. It means that I will run 3 containers. Each container you will see it will dynamically provision a slice of 2/7. Okay. Then we will delete 2 of these containers. So we will simulate a scenario where these servers we didn't need them anymore. We spin them down, and then we will have one container left, and we will see that we can then have another container that will ask for a bigger slice of 3G 20 GB, so for 3/7. And we'll see that this will work. We don't rely on any existing profile. Each job will on the fly create the partitions. There is another question here, if RunAI can be used with other GPUs such as V100. So this is a great question, George, and this is the next demo that we will show. So the first demo here, we're going to talk about how RunAI helps with using the NVIDIA MIG, but like I said previously, this MIG capability is only available with the latest and most expensive GPU of NVIDIA, the A100. However, RunAI also has its own technology that we've built here in-house that can help you fraction any type of GPU. So both the V100, but even older GPUs and weaker GPUs like T4s and K80s and even 1080s, 2080s, anything like that, on the software level. So NVIDIA provides this partitioning on the hardware level. We do it on the software level, and we will see a live demo of that as well. So let's jump and just see that the question. Do we need specific extensions of TensorFlow or PyTorch to run on these slices? So no, you don't need that. Let's go and see a live demo. So what I'm going to show you is we're going to deploy an inference server on Kubernetes. So I have a Kubernetes cluster, and we can go and see it here. If I go and run, let's just make sure that I'm on the right cluster. So it's not this one. I'm going to choose the right cluster. Okay, great. So if I run the kubectl get nodes, you will see that here I have a cluster with 3 nodes. I have my master node, I have another CPU node, and I have a GPU node. And this GPU node is a machine with an A100 GPU, and it already has the MIG enabled. So just to show you what I did here, I SSH'd into the actual GPU machine, and you'll see that if I run the NVIDIA SMI command here, it's a bit small, but let's see if I can make this a bit larger. I just want to show you that that I have MIG enabled here, you see? So here MIG is already enabled, and if I go and run this command, NVIDIA SMI mig.-lgi, it shows me the existing MIG slices on this A100 GPU. So currently I have 2 slices here already existing, one slice of 2G 10 GB, which is a 2/7 slice, and one slice of 3G 20 GB of 3/7 slices. But currently no containers are actually running on this cluster. I have these slices configured there, but nothing is actually running. Okay, I can go and run the get pods command, and I will see that I have no pods here. Now let's look at my deployment YAML. And this is a regular deployment YAML, and you'll see the only difference, and I'll show you what is RunAI specific here. But basically, this is a kind deployment, and I'm going to give it a name. I'm going to call it Inference Server Demo. It's going to run in a Kubernetes namespace called runai-project-a. It's going to start with 1 replica. And you see here, under the spec, I go and add this scheduler name, RunAI scheduler. So this is the only thing that is one of the most important things, that instead of using the default scheduler of Kubernetes, as I installed RunAI on my Kubernetes cluster, I can use the RunAI scheduler instead of the default scheduler. I can then choose the container that I want to run. So here I'm going to run this container image called Quick Start Inference Marian. So this is a Marian server, a pretty standard Marian server that I'm going to use, and it's going to run on port 8888, and it's also going to deploy a service. Just to, and this is something that I can share, but to show a bit about Marian server, I won't talk too much about it. But this is the RunAI documentation. And here, if I go to Inference, it explains a bit about this image. So this image is public, and you can look at it as well. We can look at it together. So this is the Docker file. You see, it starts with this base image of NVIDIA CUDA version 10.1 on an Ubuntu 18.04 machine. It's going to install some basic packages here, and then it's going to use again this Marian server and expose it on port 8888. So this is the server that I'm going to use for my deployment. And the second interesting thing here is that I added this annotation here called nvidia.com/mig-2g10gb1. So this means that for this container that I'm going to launch on my cluster, I want to allocate only one MIG slice of 2g10gb. So to apply this YAML file, I can run the kubectl apply -f, and then this file is called inference server mig 2g10gb. So once I apply this YAML file, it's going to deploy my inference server. And here you see I just ran a watch command on the get pods, and I see that now I have my pod running. It's now on container creating stage. And if you look here inside my A100 GPU, you see that dynamically the MIG slice of the 3G20GB that was not required anymore was removed. And I only have, the only slice that I need is the slice that I have here, which is the 2G10GB, and my container is actually running here. And just to show you, I can go and run the kubectl logs on this container. And it will show me the logs of my Marian server. I can also, I can add the -f to follow. Yes, and I see it here. So I have my first job running, right? And I see my container here, and the slice was created on the fly. Now I can go and apply my second inference server. So this is this server 2 MIG 2G10GB. So it's actually the same container asking for the same slice, and it's going to start a new container here, a new pod, and this should automatically and dynamically provision a new MIG slice on my A100 GPU once the container is up. And we will do this one more time and run another one. So you see that the idea is that instead of being dependent on some existing, see, another slice was added up automatically here and another pod is running. So I'm not dependent on some preset profile that determines the slices that I must use. I have much more flexibility as a researcher. I can, or as an MLOps engineer, I can just go and dynamically ask for the exact slice that I want for each job, for each container. So I just ran 3 containers. Can I use multiple slices at once? Yes, you should be able to also ask multiple slices at once. You saw that just here in the YAML, I only added one annotation here of one slice of 2G10GB, but you can also ask for multiple slices for the same server. Now, let's go back to my terminal. It wasn't this one, it was the second one here. Yes. Now, like I said, we want to simulate a scenario where 2 of these are terminated. We don't need them anymore. So what I can do is I can run the kubectl delete command and pass the name of my let's delete, let's say, the second and the third one. So I can delete this job, and you see that once I go and delete, it does not automatically, it will delete the container. You see that the second container is now terminating. It will not delete the actual MIG slice, because this is an expensive action. We don't want to go to the node and delete the MIG slices unless we actually need to. So you'll see that if I go, I'll delete this third one as well. This will delete the third pod, but again, it will not delete the third the MIG slice. However, if I now want to apply, just to show you, I have another deployment YAML here, which is exactly the same. I called it Inference Server Demo 4, but the only difference is that this time I'm going to ask for a different size of slice. I'm going to ask for the 3G20 GB. So this is 3/7. So just like before, yeah, not this one, sorry. I'm going to run the kubectl apply, but this time ask for this one, the 3G20 GB. And what you'll see now is that once I ask for this type of slice, it will go to the node, you see, and it's deleted the unnecessary MIG slices, the two slices of the 2G10 GB, and instead it created on the fly a new slice of 3G20 GB, and I see that my new pod is running. So this way, you can work, if you have an A100, you can work with the MIG in a much more dynamic way. And I hope this made sense. Another question I see here, how are the GPU cores and GPU memory sliced? Are you splitting cores and GPU equally? A good question. So this is, again, something that is done by NVIDIA. We just help you do it in a more dynamic way. But you can see the actual slice of the compute and the memory in this table here. And so the way that they did it, NVIDIA, is that they sliced up the memory of the A100 to 8 pieces and the compute to 7 pieces. So it's a bit weird, to be honest, but you see that this is also the terminology in the name of the slices. So the smallest slice of 1G 5 GB means that you get 1/8 of the memory, the GPU memory, and 1/7 of the compute. And the second largest slice is 2G10 GB. It means that you get 2/8 of the GPU memory and 2/7 of the compute, etc. So it explains everything here, and this is of course available online, and you can see how this works here. And I hope that answered the question. So this was the first demo. And now what the second demo that I'm going to show is, I think, even more impressive, because like we said, with the MIG, it's a great functionality, it's a great capability, but it's only available on the A100 or the A40, I think. So only if you have these specific GPUs, which are pretty expensive also, you can use it. And also it comes with some limitations. You can only slice this GPU to up to 7 slices. What we provide with Run AI is a capability that we built called fractional GPUs. And this is something that is built into our platform and scheduler. And this allows you to run multiple containers on the same GPU. And the cool thing with this capability is that it works with any type of NVIDIA GPU. So not only the A100, but also the V100, K80, T4, 1080, etc. Wait, I see another question about the MIG. Not sure if this makes sense, but can we do the slice differently than in the table, 2G 20 GB? So with MIG, no, you can't. With MIG, you are limited. You can only ask for one of these. So NVIDIA created these hardware partitions, and this is what they give you. You can either ask for the whole GPU or you can ask for one of these slices. However, with Run AI, you have much more flexibility. So of course, one advantage is that it's not only on the A100, it's on any type of GPU, but as with Run AI, it's a software partition, and you can ask for as many slices as you want and for any size of a slice. And we'll see the power of this. So let's go to our second demo, and I'm now actually going to switch to another cluster. This one. It's this one. Okay, so let's choose our right cluster. Now I'm going to use this cluster, and on this cluster, very similarly to the one before, if I look at my nodes, and here I have 2 GPU nodes, one master node and one CPU node. And just to show you, I'm going to run a quick command called run AI top node. This is a CLI that we created, but it just helps us easily understand what we have on our nodes. So you see that on my GPU nodes, I have 2 GPUs on each node. It's actually K80 GPUs, so pretty weak and not something very new. So I have a total of 4 GPUs, 2 GPUs on each of these nodes, and I have my master node of the cluster, and I have a CPU node. Now, if we look again on our files here, what I'm going to deploy now is, again, a very similar deployment to what we have before, the same inference Marian server running on the same port. And this time I'm going to ask, I'm also going to point to the run AI scheduler, but I'm going to start with something that is not impressive or not something that is new or nothing special. I'm just going to ask for the regular way that you would ask for GPUs when running on Kubernetes. I'm going to put the resources section here under the spec and ask for one NVIDIA.com GPU. So if I go and run the kubectl apply, time it's going to be, oh, wait, I'm not in the right directory. Documents, yes, now I'm here. So kubectl apply, and it's called this one, server 1 GPU. It's going to deploy my Marian server on my cluster, and you'll see that it's going to be deployed as a pod here, and I see my pod running here, and just like before, I can run the kubectl logs on this pod and specify the namespace. And I should be able to add the -f to follow, and I see that my server is running and it's listening on port 8888, so it's ready to serve requests. But now let's do a more interesting thing. So what we can do with run AI is I can run another inference server, and again, the same container, and you see that I don't need to make any changes to my container. I don't need to make any changes to my code. I don't need to make any changes to TensorFlow or PyTorch. I don't need to spin up any hypervisor, nothing. The only thing that I need to do is ask for a fraction of a GPU. So everything is exactly the same as before, but this time, instead of asking for 1 GPU, I'm going to ask for half of a GPU. So let's go and deploy this server. You see, I call this file inference server 0.5 GPU, and you'll see that it's going to deploy another deployment, and I'll see it as a pod here. Okay, and just like before, if I look at this new pod, it will show me the exact same logs. It's a regular Marian server, and I see that it's running and it's ready to serve requests. But now let's see the difference. So if I look at, I will go inside the pod itself, so I can run command called kubectl exec-it, and I can go and choose the pod that I want to exec into. So let's start with this pod that is the first one that we ran and ask for a whole GPU. And once I'm inside this pod, I can run the NVIDIA SMI command, and you'll see that this pod is running on, like I said, on a single Tesla K80 GPU, and it has all of the GPU memory that comes with the K80, right? Because I asked for a whole GPU. However, if I exit this pod, and then I go and exec into the second pod, yeah, so I'll just change the pod name here. And then once I'm inside the second pod that asks for only half of a GPU, I'll see that this pod is also scheduled on a single Tesla K80, but it has only half of the GPU memory allocated to it. So you see, I just now live sliced up a K80. And obviously, I can do the same thing to a V100 or to any other type of GPU. And here I did 0.5, but you can ask for 0.1 or 0.2. You can even explicitly mention the amount of GPU memory that you need. If you need 1 gigabyte of GPU memory, you need 200 megabytes of GPU memory. So this way you can run much, and many more workloads on the same GPU. And why is this so important? So if we go back to our slides here, you can see an example from one of our customers that actually benchmarked and tested our solution. And this customer is an enterprise company that has a heterogeneous cluster with different types of GPUs. So they have both T4s, V100, and A100s. And what they saw is pretty amazing. They saw that they have, by the way, some real-time AI translation model that they're running using Run AI on fractions of GPUs. And they saw between 2x to 8x increase in the throughput. So when looking at the T4, you can see that just running a single server, right, without Run AI, without fractions, a single inference server on the T4, the throughput was about 16 requests per second. Then when running 2 servers, so to using 2 fractions, it goes from 16 to almost 30. But then running 3 fractions goes to 35, and they reach the peak by running 4 servers. So so slicing up the T4 using the Run AI fractions to 4 slices brought more than 2x gain. So from about 16 requests per second to about 40 requests per second. On the V100, it's even more significant. So if you think about it, as you have more powerful GPUs, you can get much more throughput and lower latency because you can slice them up to even more slices. So with the V100, it's if you think about it, it's a real waste to allocate the whole V100 to a single, inference workload. So you see that with a single inference workload without fractioning, again, you get about 16 requests per second, but they were able to fraction the V100 to 8 slices and get more than 50 requests per second. So more than 3.5x gain. And with the A100, it's nuts. It's 8x, right? And if you think about it, the A100, even though it comes with the MIG capability, MIG only allows you to slice up the A100 to 7 slices. But with Run AI, they sliced it up to 12 slices, and they got even more throughput. So going from about 18 requests per second to around 120 requests per second. And like we said in the beginning, higher throughput also translate directly to lower deployment costs. You can run and process more requests on the same hardware. And so meaning you can run and process more requests on the same cost. So this has a direct and significant cost optimization. So this is pretty much what I wanted to talk about today. I hope it made sense. We have a couple more minutes if anybody has any questions. Thank you, Maja. I'm glad you enjoyed the session. And you know what, I'll just post maybe some useful links on the chat. So if you want, you can look at it later. Is the GPU, there's another question from Christian, is the GPU bandwidth a bottleneck? Also, what's the difference between training job and inference job? Oh, okay, see a few more questions. Great, so we have a few minutes, so I'll try to answer as many questions as possible. So let's start with this question. What is the difference between training job and inference job? So training job, let's go back to the beginning. Yeah, and I think we just, yeah, time is up, but these were great. Thank you very much for joining today. Again, I hope that was helpful.
Thank you very much, Guy, for such an interesting talk. That was a really good session. And I appreciate you take the time to prepare the live demo. Everything went smoothly. Thank you very much.